All right, let's dive in. Today we're talking about something that is, quite literally, the backbone of almost all the software you use every single day: object-oriented programming. We're going to break down exactly what makes this approach the essential blueprint for all of modern technology. But first, let me ask you something. Have you ever wondered how a massive, complex video game, with thousands of different characters, items, and rules, is even built? How do developers keep all of that from collapsing into a completely tangled, unfixable mess of code? Well, the answer is this really elegant, really clever way of thinking called object-oriented programming, or, as you'll usually hear it, OOP. It's the secret sauce that keeps these huge software projects organized, efficient, and actually possible to maintain. So to really get a grip on OOP, you've got to start with its two most fundamental building blocks. We're talking about classes and objects. This is basically where we learn to read the software blueprint. Okay, so first up is the class. The best way to think about a class is as a blueprint. Super important. It's not the thing itself, but the idea of the thing. So if we were in a car factory, the class is the master design schematic. It's the document that details exactly what a car is, what it has, like wheels and an engine, and what it does, like accelerate and brake. Right. So if the class is the blueprint, then an object is the real deal. It's the actual tangible thing that gets created from that blueprint. Back in our factory, this is the physical car rolling off the assembly line, the one you can actually see, touch, and drive. It exists because it was built using that master plan. And this, right here, just nails the core difference, doesn't it? On the left, you have the class. It's the abstract plan, the concept. And on the right, you have the object, the concrete, real thing you can actually work with. I mean, you can't drive a blueprint, but you can definitely drive a car. And here's the crucial point to lock in. From that one blueprint, that one class, you can create tons and tons of cars, which are all objects. And each one of those cars might be a little different. Maybe one is red and another is blue, but they all share that same fundamental structure defined by that one single blueprint. Okay, let's build on that. Our next core principle is where OOP gets really smart and efficient. We're talking about inheritance, and it's all about one simple, powerful idea. Don't reinvent the wheel. So what is inheritance? It's basically this awesome trick where a new class can be based on a class that already exists. It just automatically gets, or inherits, all of the properties and behaviors from its parent. The original is the base class, and the new, more specific one, is the derived class. Let's go back to the factory. Imagine we've got our standard car blueprint, right? Now, let's say we want to design a sports car. Well, instead of starting completely from scratch, we can just create a new sports car blueprint that inherits from the original car. Boom! It automatically has wheels, an engine, and seats. All we have to do is add the cool new stuff, like a spoiler and a turbo engine. And why is this such a big deal? Well, the huge advantage here, the absolute game changer, is reusability. By building on code that already exists and works, programmers can save just enormous amounts of time and effort. Plus, it keeps everything way more consistent and reliable. All right, next up, we've got a concept that's all about safety and simplicity. It's called encapsulation, and a great way to think of it is like a protective bubble you put around your code, keeping all the complicated bits safely tucked away. So, encapsulation is basically the idea of bundling data and all the functions that operate on that data together into one neat little package, our object. The best analogy for this is your car's dashboard. You don't need to know how the engine is firing or how the transmission is shifting gears. You just get a simple, safe interface, a steering wheel, and some pedals. All that mind-boggling complexity is hidden away, or encapsulated. So what does this get you? Well, by hiding those inner workings, encapsulation protects the data from being changed by accident from the outside. And this makes the software so much more secure, way more robust, and a whole lot easier to update and maintain later on. Okay, for our final pillar, we have a bit of a fancy-sounding word: polymorphism. But don't worry, the name is way more complicated than the concept itself. It literally just means one name, many forms. So, in plain English, polymorphism just means you can perform a single action in lots of different ways, depending on what object you're doing it to. The interface, the action, is the same, but the result changes. Okay, But what does that actually look like back in our car factory? How can one single action have a bunch of different forms? Well, imagine we have one single command, start engine function. If we use that action on a gas car object, the engine roars to life and starts burning gasoline. But if we use that exact same action on an electric car object, a silent motor just hums to life, pulling power from the battery. See? This same action produces a completely different result, and it's perfectly tailored to each specific object. This is what makes code so incredibly flexible and dynamic. That right there is the power of polymorphism. So, we've covered a lot of ground here. Classes, objects, inheritance, encapsulation, and polymorphism. Let's pull it all together now and talk about why this whole way of thinking, this OOP paradigm, is so incredibly important for building modern software. So, when you boil it all down, what are the big takeaways? Well, OOP helps us organize crazy complexity by breaking huge problems down into simple, manageable objects. It promotes reusability with inheritance, which saves a ton of time. It enhances security with encapsulation, protecting your data. And it increases flexibility with polymorphism, letting your code adapt to just about anything. When you put all these principles together, you get this incredibly powerful blueprint for building robust, scalable, and maintainable software. These are the tools that let developers build the amazing and complex digital world that we all live in. So really, the only question left is, now that you understand the blueprint, what would you build?